Yeah, so first of all, thank you for organizing this conference and also for giving the opportunity to talk to you. This is ongoing and joint work with Franz, Monica, and Henry. And it's about approximation properties and characterization of operator modulation spaces. And well, we have, so that the central transform of study, or the central underlying transform, is the operator short-term Fourier transform, which we have already encountered several times so far. Well, basically you take your window operator phi, Hilbert-Schmidt, and you say that the STFT of some other Hilbert-Schmidt operator f is simply, by definition, well, you compose f with the adjoint of the time frequency shift at c, and then compose this with the adjoint of your window operator phi. And then, as we have already seen in Henry's talk, this gives you a square integrable Hilbert-Schmidt valued function on phase space, and in particular a bounded operator from the Hilbert-Schmidt space into the Hilbert-Schmidt valued L2 space. And then you can consider the operator modulation spaces. So a specific choice of our window operator would be the L2 normalized Gaussian function tensorized with itself. And if this is your window, then you can define the operator modulation spaces simply as the set of all tempered operators whose short-term Fourier transform is in the Hilbert-Schmidt valued LP space. Here, for simplicity, I simply ignore the weighted versions of the operator modulation spaces. Yeah. And the norm, the MP norm is simply the LP norm of the operator STFT. And this is just a nice fun fact or a reminder for people like me who don't really come from quantum harmonic analysis. So these operator modulation spaces kind of perfectly fit in of some other well-known operator spaces on L2. And on the other hand, they are also the operator valued analogs of the function modulation spaces. And since they are in many purposes kind of natural choices for, let's say, test functions or whatever, as we've seen in the previous talk, Feichtinger's algebra appeared out of nowhere. So it's kind of interesting to consider the operator valued analogs. And what we will do now is we ask ourselves the following question. So how and how well can we approximate some given f from, let's say, M1 or MP via simpler or, let's say, more convenient means? And, well, this is, of course, somehow a vaguely formulated question. So maybe, let's rephrase to, how can we find a sparse approximation of some given f via elements in, let's say, in a larger pool, the Hilbert-Schmidt operators, using a prescribed set of atoms. So this would be called a dictionary, and we will actually use an operator dictionary. And an observation from the literature is that in the function valued case, that sometimes, or if you are in the right setting, then best M-term approximations can be, let's say, naively obtained via frame type expansions if the frame you're dealing with is well localized. But now here we are in the operator valued setting, so we won't consider frames, but G-frames, which are kind of a generalization, and you can think of G-frames as operator valued frames. And the idea is to consider some specific, very well-behaved operator valued frame, or G-frame, which at the one hand describes my operator modulation spaces, and at the other hand is the link to get approximation type results for operator modulation spaces. And here's a short reminder on G-frames if you haven't seen them so far. And I formulated this slide in abstract Hilbert space. just to keep in background, so we will consider H to be the Hilbert-Schmidt operators on L2. This will be our goal, but for simplicity, maybe let's just say H for now. So a countable family of bounded operators on H is called a G-frame if there exist positive constants A and B such that, well, you apply to your signal F or to your operator F then later, you apply the operators U lambda, and this is a Hilbert space valued sequence, and if the L2 norm of the sequence is equivalent to the Hilbert space norm. So basically you have some kind of operator valued frame. And this is, so the G-frame inequalities are equivalent to say that the G-frame analysis operator, which, well, again, which maps a vector F to this H-valued sequence, that this operator is bounded and injective and has close range. If you know frames, then you know that you can take the joint operator, and this is called the synthesis operator. And in fact, the G-frame inequalities are equivalent to saying that this synthesis operator is bounded and surjective. And then what are you doing next? You compose the two. This is the frame operator, and this is then a well-defined, well, it's bounded, it's positive and invertible, and if you have an invertible operator, of course, you look at what happens if you compose S with its inverse, and if you're lucky, then, this is formulated in a stupid way, but if you do that, then you get a possibility of perfect reconstruction for any vector in the Hilbert space. This is recap of G-frames and of frames if you want. And what we will consider is a frame which has an additional property, a G-frame which has an additional nice property, namely that it's, this is called the canonical dual frame. So the operators in blue are called the canonical dual frame. And we will consider a G-frame which has some additional nice property, namely it's S-localized. So what does this mean? S-localization means that there exists a uniform constant C such that the operator norms of these compositions are bounded by this polynomial expression. So in some sense, you could say that if your G-frame elements are in some sense far apart, then they correlate very little in some vague sense. You can think of the index set lambda as a lattice, for instance. Yeah? It should be, later we will see it should be a relatively separated set. Yes, so for now, so here it's everything, but in order for the theory to work, it should be a lattice or some relatively separated set, yes. And similarly, if you take another G-frame, W, then you say that U and W are mutually localized if the same holds, if you replace U mu star with W mu star. And conceptually, maybe easier to grasp is to rethink of this definition as follows. Just in the previous talk, we heard that bounded operators on L2 are given by scalar matrices, and here this is basically, these are precisely the entries of the operator valued matrix which describes the G-gram matrix. So we can compose synthesis with analysis. This is then a bounded operator on the H-valued L2 space. It's described by the so-called G-gram matrix, and these are precisely the entries of the G-gram matrix. And this condition says that your G-gram matrix belongs to the so-called Jaffa class of BH-valued matrices for which this supremum condition is satisfied. So this is basically a weighted supremum norm. And this Jaffa class has actually some very nice property. It's actually one of these spectrally invariant algebras which are mentioned that pop up in harmonic analysis. So this is one of the examples. And in the scalar valued case, this is known as Jaffa's lemma, so property 3. We did the same for operator valued matrices because this pops up in this setting. And well, the Jaffa algebra or the Jaffa class has the following properties. It defines a bounded operator on the Hilbert space valued LP space, not only for P between 1 and infinity, but actually also for every P which is larger than 2D over S. And here we assume that S is larger than 2D. So this is also true this can be achieved for values smaller than 1. Then it's a second property, it's a unital Banach-Star algebra via matrix multiplication and involution matching taking adjoints in BL2. And third property, which could be seen as an operator variant of Jaffa's lemma, which says that JS is inverse closed in BL2. And due to these nice properties, we can deduce the following. So if we are given an S localized frame and that the K parameter S is large enough, then we can also show that the canonical dual G frame is S localized. And we can also show that U and its canonical dual are mutually S localized. I'm not going into the proof details here, but this is really due to these highly non-trivial properties of the Jaffa algebra. But we can do more. We can, so given an S localized G frame, we can also define associated Banach spaces. How do we do this? So first of all, we need the same assumptions as before. Let's say lambda is a lattice and the decay parameter S is large enough. Then we consider the space H00. So this looks a bit wild, but in the end, this is the image of the finitely supported sequences with values in H under the action of the synthesis operator. And if you recall your frame knowledge or even your G-frame knowledge, for G-frames, you know that the synthesis operator viewed as an operator from L2 into H is surjective. So, and since this is dense in L2, and since this is continuous and its L2 image is the whole space, this is actually a dense subspace. So the finite synthesis series, so to speak. And on this dense subspace, we can actually define a new norm for values in the range I mentioned before, namely by, okay, I consider the analysis operator associated with the canonical dual G frame applied to F. And instead of the L2 norm, I consider the LP norm. And you can show that this is really a norm and a quasi-norm for P smaller than 1. And if I now take the completion, I obtain a Banach space or a quasi-Banach space. And yeah, that's the definition of what I would call the coorbit space associated to my G frame. And then you can show, okay, actually the definition of the norm, you can also obtain an equivalent norm by just considering the analysis operator associated with the given G frame and not the canonical dual G frame, and another norm equivalence. And you can also show that your perfect reconstruction, which initially holds true in the Hilbert space, also converges for all elements in your coorbit space with unconditional convergence. And another description, you can also show that this coorbit space is the completion of this space, so the space of all Hilbert space elements whose analysis coefficients are in LP with respect to the same norm as before. This is everything is the same space. And maybe a short, there's also a way to define the space for P equals infinity, but it's very technical. The simplest way would be to say it's the dual of the coorbit space with exponent 1. And this characterization holds for P less than infinity. Okay, never mind. So now we think again about the setting from the introduction, about operator modulation spaces. They are described by the Hilbert-Schmidt valued LP norms of the STFT. So what we are aiming for is to find a G frame for the Hilbert-Schmidt for HS, whose analysis coefficients would then be samples of the operator valued SDFT. And this is basically the idea. Then we could observe that basically we are almost, this has been observed in literature, that if you take the family of operators given by, so here this is again the Gauss tensor Gauss window, and compose it with the time frequency shifts at lambda and take the adjoints, that this is a G-frame for L2. We want the G-frame for the Hilbert-Schmidt operators on L2. But there's a trivial trick how to raise G-frames from L2 to Hilbert-Schmidt operators for L2, namely by, well, you give me a bounded operator on L2, I say, okay, I define, so the operator is called A, I define LA simply by left composition, and this is, of course, by the ideal property of compact or of Hilbert-Schmidt operators in bounded operators. This composition will be a Hilbert-Schmidt operator again, so this LA is then really a bounded operator on the space of Hilbert-Schmidt operators, on HS, which is our Hilbert space of interest. And then it's really not easy to show that this family then, it's easy. It's not, no, it's not hard.
Now it's easy.
Yeah, now it's easy. This is to show that this is a G-frame for our Hilbert space, which we are interested in. But we want to show another property, which I advertised for, I don't know, 10 minutes. We want to verify that this is an S-localized G-frame, and this is indeed true. So the result is there exists a full rank lattice such that this family of operators is a G-frame for HS. And don't go through all the verifying details here, but in the end, if you do the computation, what you end up with is the function SDFT of the Gaussian with window Gaussian at the point lambda minus mu. And this is using that the Gaussian is, let's say, a Schwarz function, and therefore contained in all weighted M-infinity spaces, where here the weight Vs is the polynomial weight. Then we get the desired estimate. And now, okay, now everything is set up. I guess the next natural thing to do is consider the coorbit spaces associated with this G-frame. And in fact, we could show that these coorbit spaces are precisely the operator modulation spaces with equivalent norms. So this is one convenient way to describe this, at least for someone who is rather used to G-frames than to quantum harmonic analysis. But I also told you in the introduction that if you work with localized frame type expansions, then you can rather easily obtain approximation theoretic results. And this is what we're going to do next. But before that, recall that, so here this is for p between 1 and infinity, but I said to you that we can also define these coorbit spaces as quasi-Banach spaces for exponents p less than 1 if, where is the, so we said that these spaces are defined for all p which are larger than 2d over s. But we just have seen that we have S localization for S as large as we want. So in particular, we can consider all values, all exponents p between 0 and 1. And this is therefore a natural way to extend the definition of an operator modulation space for exponents smaller than 1. So I simply set MP as this coorbit space, and it as this coorbit space. Now we consider approximation type results. So here we, instead of a vector dictionary, we consider an operator dictionary. And this is basically, a family of bounded operators on our Hilbert space is called an operator dictionary if, again, is the image of the finitely supported sequences under the synthesis operator is dense in the Hilbert-Schmidt space. So if you recall, every G-frame is an operator dictionary. And of course, we will work with the G-frame from before and consider it as a dictionary. And then you can define these sigma m. They are not spaces. They are they're not closed under addition. Actually, they are sets, or I don't know how you call these. Basically, as those elements from here, which contain at most m many terms. And then we also are interested in what is in the literature known as the best m-term approximation error of f. And we say that, okay, we want to know what is, in some sense, the best approximation of some given f using some g from our set sigma m. And I won't read this, but this is kind of, if you have a dictionary, then you can, or an operator dictionary in this setting, then these are the kind of simple properties that you can show. Don't focus about too much. This is just a natural thing to do. And in particular, more importantly, you can then define the approximation space AP alpha, which is given as the space or as the set of all F Hilbert-Schmidt, for which this norm, or actually quasi-norm, this norm is finite. So here, this is the best m-1 approximation error. And then, well, this is some kind of a weird norm if you haven't seen it before. But this is a natural way to measure approximation rate in some sense. Yeah, that's the next slide. So this is why I bothered to show you this weird lemma from before, which I showed you for only 5 seconds. Then you can use this lemma, and then you can really show that this is a well-defined linear subspace of HS, and this beast is really a quasi-norm. So you can really measure things with that. And then we could then show that for exponents p less than 2 and for alpha equal to 1 over p minus 1/2, that we have the following continuous embeddings. So the operator modulation space MP is continuously embedded in this approximation space AP alpha. This is basically our contribution, and that the second embedding follows from general principles which you find in a book on approximation theory. And I think I don't go through the proof details here, but the main takeaway is that when you specifically consider, so we had an embedding, so we consider the infinity approximation norm of f, given by definition, and we use the two embeddings and know that this is bounded by a constant times the MP norm of f. And this in particular means that the best m-time approximation error somehow, well, you have some polynomially decaying estimate in some sense, a continuity estimate. So in other words, this means that any f from your operator modulation space can be approximated by m terms with this approximation rate alpha given by 1 over p minus 1 over 2. And now we also, if you think about it for a few seconds, if p is very small, so let's say close to 0, then this is a really this decays really fast. So this is also the reason why you are interested in approximation well, why you in approximation theory consider LP norms for P smaller than 1, actually. So for small p, you could say this somehow is vaguely formulated sparsity promoting. And one way to achieve this, this was in the proof on the previous slide, which I don't show you in detail. But basically what you do is you consider your analysis coefficients of the G-frame, which, sorry, I should have mentioned it sooner, by the way, is precisely what we wanted. So these are the samples of the operator STFT. You measure the norms, you pick the m largest ones, and you use these coefficients and consider, in some sense, the truncated G-frame reconstruction series. So you have perfect reconstruction, but you only sum up the those which correspond to the m largest ones, and this gives you one possibility of to achieve this. And finally, this is also what we found in the literature, which has been done for frames. We could also consider the sparseness class associated to some general G-frame, and if P is less or equal than 2, then this is defined as the set of all Hilbert-Schmidt elements, set of all elements in your Hilbert space, which can be represented via the synthesis operator using an LP sequence, an HS-valued LP sequence. So again, for P close to 0, this is again in some sense close to a sparse representation, and this is why this is called the sparsity class, and the norm is given by this expression. And the theory of localized G-frames gives you for free that this is again the coorbit space, or we defined it for P less than 1 as the modulation space. So we have that the sparsity class or the sparseness class is again the operator modulation space MP. And having said that, I'm done, and I would like to thank you for your attention.
Yes, thank you for the introduction, and also thank you to the organizers for even giving me the opportunity to hold this presentation here today. This is based on joint work together with my PhD supervisors, namely one of them is Ulrich, who is sitting here today, and the other is Makoto Yamashita. And today I'm planning to talk about something that we call a Duflo-Moore theorem in a very particular von Neumann algebraic setting. And I'm basically trying to convince you today that this actually has something to do with quantum harmonic analysis, and in fact something which I think very fundamental. So I thought I wanted to start with something that's, I think, very familiar, at least to the experts, namely with Werner's original theorem, 1984, quantum harmonic analysis on phase space, that basically started the theorem and the theory. And yeah, so here I'm showing you a screenshot of Werner's paper, and not just, and I highlighted a particular result, and not just any result, it's actually the very first result in the paper that you find. It's a very innocent looking lemma, and I'm not making this up. Werner himself calls this the cornerstone of the entire theory. So I hope with that I can already convince you somewhat that this might be interesting to take a look at. and maybe to see in which other settings we can have like similar statements. But maybe let's read it together. So Werner's considering two trace clause operators of his setting, and then he's stating a certain integrability of a certain function. And I think after the past 3-4 days now, many of you will probably recognize this as almost already being the convolution of two operators. Well, and he's not only stating the integrability, but he also evaluates the integral. So, well, and so basically the whole talk will be roughly about this lemma, and I think we will progressively get maybe more involved. So I think it's good to start with something particularly easy, something that we're all very familiar with, namely with the convolutions of functions, actually. And you can all now imagine your favorite setting in which you want to write down a convolution of two functions. Here I picked a setting of a locally compact group. You don't need to know what this means. You only need to know that this is like a nice framework in which you have something called a Har measure. It's like a left invariant measure on this group. Well, there's also the modular function, which somehow is the positive function that relates like the different right translates of a fixed Har measure. Whatever, we define the convolution like we're used to, like here, for example, you can do it for many pairs of functions. And what we are interested in today is taking the integral of the convolution. And this is a very easy application of Fubini's lemma, right? One integral goes inside the other. Then you use the invariance of the Har measure. What happens? The integrals split apart. And there's also another fact that we saw several times, or I think on Monday and Tuesday, which we usually refer to as Young's convolution inequality, right? So I don't want to read it, but for different integrabilities of the two inputs, we get a certain integrability of the output of the convolution. And I've written it down maybe in a very peculiar, strange way, you might argue. But I hope in the end of the talk, you will understand why exactly I'm writing it in this form. And notice that also the modular function is appearing. The check is exactly what you expect. It's the inversion of the argument. No. So, sorry. Let's go to Werner's setting. And I'm sorry maybe to the experts for abstracting away almost every of the nice properties that we know about like the quantum harmonic analysis setup. What I'm only interested today is basically what we need for stating this convolution lemma. Well, so Werner's considering a particular projective representation, right? I'm not really interested in exactly how it looks like. I'm not even writing it down. What I'm only interested in here is the action that it induces on the bounded operators. Well, as we are used to by just conjugating with the unitaries. And in Werner's definition of the convolution, there's also this parity operator showing up. But as you already saw, like in this first screenshot, Werner is not writing this down, at least for this integrability lemma. And you can convince yourself that you can make this statement with or without the parity operator in this case. So I invite you all to ignore this, basically for the remains. Okay, whatever. So Werner says, well, this is integrable. We can evaluate the integral. We also have this version of Young's convolution inequality, right? And notice here, for example, the modular function is not appearing because, well, our group is a nice abelian group. Well, so far so good. Now let's go to something, I promised you generalizations of this lemma. So one of them I picked, a very notable one, is based on a paper of Berge, Loew, and Skretningland, right? I think it's actually called quantum harmonic analysis, affine quantum harmonic analysis. And again, there's many nice things appearing there, but the only thing that I'm interested in here is, again, the way this now non-unimodular group, in fact, the affine group or AX plus B group, as you might know it, is, first of all, represented on a certain Hilbert space. I don't care. I'm only interested in the action. Again, we define it exactly like before, and then we can write down a convolution. Well, you might object here, this, where's the parity operator gone? Well, if you read the paper, you will see that this representation is not precisely the one that I want to consider here for this convolution. It basically differs by an additional minus sign. And well, so what happens now in this more involved case, you might argue, what is this effect of taking like a non-unimodular group now? And it's stated here, suddenly it appears that not all pairings of two trace class operators lead to integrable convolutions anymore. Well, what you need to consider is a very particular, densely defined positive unbounded operator on the Hilbert space now. Yeah, I've written it down here in the paper. They call operators admissible if a certain way of conjugating with this unbounded operator leads to trace class operators. Yeah. So there's also different subtleties involved here. For example, in the paper, they have to deal with certain domain compatibility conditions to give this a valid sense in which we can interpret this conjugation with this unbounded operator. But yeah, let's forget about this for now. Let's just accept the fact that for such admissible operators, we can still write down the operator convolution and we get a familiar looking formula for evaluating this integral. Maybe one remark about this, they also can state like analogs of the Young's inequality. Again, this conjugation with this unbounded operator will show up. Yes, let's just leave it like that. There's probably one question in all of your minds. Where is this strange unbounded this strange unbounded operator coming from? And the answer you will get when considering, instead of T1 and T2 here, just very simple rank 1 operators. So what happens if you plug in rank 1 operators? I wrote it down here. Then you essentially recover a theorem of Duflo and Moore, 1967, which states that given a very particular irreducible representation of a non-unimodular group, which satisfies a property called square integrability, in that case, there will exist a densely defined unbounded operator, positive operator, on this Hilbert space that you're representing on, and it will determine when exactly two matrix coefficients will be orthogonal to each other. I think this relation is usually called like the orthogonality conditions. Yeah, and you can, from this formula also by setting C1, C2 and eta1, eta2 the same, you can essentially already now guess what this square integrability condition will be. But we will get to that in a minute. One thing I want to say is if, for example, the group happens to be unimodular, if the modular function is just constantly 1, then not only does this unbounded operator become much less scary, it's actually a bounded operator, and it will in fact be a constant multiple of the identity, and we can even express what this constant multiple is. It will be the formal dimension of this representation that we're considering. Yes, so this maybe also answers the question, why am I constantly writing d to the minus 1/2? Well, I want to basically ensure this, this condition of this nice, how should we call it, maybe normalization. The formal dimension, it's the formal dimension of the representation, as far as I'm aware of. I'm also certainly no specialist for representations. I would have to look it up myself, how exactly it works. But maybe we can clear it up afterwards. One more thing I want to say is there exist generalizations of this, of this whole setup by where like the original group that Werner was considering is now replaced by arbitrary locally compact groups, which are represented in a particular way, namely for, again, square integrable, irreducible representations. So this has been, there are nice expositions for the cases of locally compact abelian groups and general locally compact groups by Simon Halfdanson, for example. Okay, so the talk would be over if we would stop there, but I'm here for even further generalizations of this fact. And for this, I invite you now, and maybe this is the only message I want to transfer today, is I want to invite you to not think so much anymore about this, really this representation that we are using, but I want to invite you to rather think of in terms of the action. So I wrote it down here again for the third time now, and I want to make some almost trivial statements about this action. The first one is very simple. This action is actually trace preserving. Well, this is just the effect of it's just due to us taking a unitary representation, right, and using the trace property. This is easy to see. The second one translates to the irreducibility of the action. This is also fairly well known that this action for irreducible representations will become an ergodic action. If you don't recall what ergodic means, it's basically, it's a condition. It's the condition that I think the stabilizers of this group are trivial, or simply saying, imagine your favorite element being translated in all possible way that the group offers. If your favorite element stays fixed under all these translations, then it must have been a scalar multiple of the identity. That's called ergodic. And the last thing is, what is this strange square integrability that all these setups have to assume their representation to be? Well, I don't want to tell you exactly what it means, but I already want to translate it into the language of the action that I invite you to think about. Namely, we can spell it out in this case as the existence of at least one non-trivial pair of two operators, two positive operators, for example, such that this integral, which will basically be the integral of our convolution, is finite. Right? If this is violated, this is somehow boring, because then either all these integrals over the convolutions will either be all zero or infinity. So now we are almost ready to finally state this theorem that I'm evolving around. But if you remember the title of the talk, it has something to do with von Neumann algebras, and I want to give everyone the chance to even understand the theorem. So let's quickly do a recap of what these definitions were. So, well, if you've never come across the von Neumann algebra, you can, for example, define it abstractly as just a Caesar algebra having a predual, but maybe it's much better to think of it in a very more concrete way. Think of a unital star subalgebra that's closed in any of your favorite operator topologies except the norm topology. So one example of von Neumann algebras is, for example, the bounded operators, no surprise here. But you can also, for example, ask what would be the commutative von Neumann algebras. And there you will find, well, they all look like essentially bounded functions on a certain measure space, I think locally compact Hausdorff space or anything like that, acting by function multiplication, pointwise multiplication on the L2 space. Okay, so now I hope we have a grasp of what a von Neumann algebra is. There will also be the mention of a so-called affiliated operator. If you recall von Neumann's celebrated bicommutant theorem, it basically states that if you have a von Neumann algebra and if you have a bounded operator that commutes with everything that commutes with the von Neumann algebra, that's called the commutant, then it must be in the von Neumann algebra itself. If you now put this condition on an unbounded operator, densely defined unbounded operator, then you get what's called an affiliated operator. And so this is maybe a notion of, well, this strange operator maybe behaves in a way similar to elements in the von Neumann algebra. You can also, for example, imagine it as being made up out of projections coming from the von Neumann algebra. Okay, maybe a last thing that I should mention is there's the notion of a so-called weight on the von Neumann algebra. Let's simply say for today it's a linear map from the positive elements of the von Neumann algebra to the extended positive numbers. So it can take infinite values, in fact. If your weight happens to have only finite values, then we call this a finite weight. But if, let's say, the set of elements where the weight takes finite values is large enough in the sense I've written down here, then we call this a semi-finite weight. And there's also now analogs of traces on the von Neumann algebra. So a trace will just be one of these weights, which has the cyclicity property that we are so used to from the ordinary trace on the bounded operators. Okay, and now we're finally ready to state the theorem that I've been talking about. So let's read it together maybe carefully. I want to consider a von Neumann algebra with, in fact, a semi-finite trace. And I want to require that this von Neumann algebra in this setting is now represented in something called the standard form. You can imagine being acting on its own Hilbert-Schmidt operators, right? So there are analogs of LP spaces for the von Neumann algebra if you, for example, are given a semi-finite weight, which mirror the Schatten P spaces. Okay, so let's agree on this setup, and let's imagine a locally compact group, in fact, acting on this von Neumann algebra. And not acting only in any old way, we want exactly these three conditions that I mentioned earlier. Namely, we want to assume that this group action is, first of all, trace preserving. We want it to be ergodic, just as mentioned before, and we also want to assume it to be square integrable. Maybe we could also give it a new name, but we just stick to this old vocabulary given from the representation case. And we want to now say this action is square integrable if the analog of the convolution that we want to define is now integrable for at least one pair of non-trivial, let's say positive elements at least. Okay, and now the theorem states what? We claim or prove that there exists in fact a unique, densely defined positive invertible operator D that is affiliated to the von Neumann algebra, just in the sense of before. And it will now again, as in the affine quantum harmonic analysis, be the one determining which operators you're allowed to take for a convolution to be integrable. Well, I didn't write anything about admissibility here. Remember, these weights were designed to intentionally take infinite values. So if any of these quantities right here takes, happens to be infinity, then we want to interpret this as infinity equals infinity. So we would, for example, call Y, the positive element Y here, and maybe admissible element if a certain way of conjugating with this densely defined operator happens to be in the trace class of the von Neumann algebra. Yes. So again, there are many finicky things about defining, first of all, what this strange conjugation should mean. And at least for positive elements, you can write it down very nicely. I should say there are, again, analogs for this Young's convolution inequality. It will probably not surprise you that, again, this unbounded operator will appear in all of them. I didn't write it down here. It's basically recovering the old statements. Maybe I should make that super clear. So if you consider now, for your von Neumann algebra, again, the bounded operators, and you consider your action being given as the unitary conjugation by the representation that we're always assuming in the quantum harmonic analysis case, then you exactly recover now this Duflo-Moore theorem, as we call it, or the integrability lemma, or Moyar's identity, whatever your name is for that. This unbounded operator has, again, certain particular properties. For example, if our group happens to be unimodular, for example, as in Werner's case, then this densely defined operator is not scary anymore. It will be a constant multiple of the identity. Well, so how's my... Okay. I mean, I don't want to overdo the time so much, so I'm not showing you the proof. But maybe one more thing that maybe answers the question that I almost stated in the beginning is, what would happen now? I mean, we have now the freedom to plug in any von Neumann algebra that we want. So what happens, for example, if you were now to plug in the commutative von Neumann algebras, right? The commutative von Neumann algebras, which essentially look like function spaces. Well, your trace will be the integral. So this, what we call, what I here call the convolution, will essentially look like the ordinary convolutions of functions again. Well, one function and the other function with argument inverted, because, again, no parity operator in this story here. So what does this integrability lemma boil down to? It boils exactly down to the integrability of regular functions. And it will not surprise you that in this, maybe it will surprise you, it surprised me, that in this commutative von Neumann algebra case, we can actually say what exactly this Duflo-Moore operator should be. It will be exactly the modular function. And with that, I will skip over the proof. Maybe you can ask me later if you're super interested in. I want to close and thank you for your attention.